As far as functions go, we have all those representations. We've got the algebraic representation, arrow diagrams, graphs, however you want to do, work with it. What we're going to start here is to look at, to classify functions into particular types. We're going to have to know types because eventually I'd like to talk about the inverse under composition. We have to have some specific types of functions to do that. We'll break it out in terms of like putting them into particular classifications. Then we'll do some special functions that everybody needs to know. Then the next section, which we'll talk about, which is sequences and series, is functions that are of a particular type that we're interested in. So we're just going to break it out to a bunch of these things. So functions are things that map a domain to a codomain such that every element of the domain goes somewhere, and when it goes to 1. On the other hand, if we would start to restrict the codomain, we have different sorts of behavior. One idea that we can talk about is what's called a one-to-one function. So this is still a function, but the idea behind a one-to-one function is that when I map an element, a pre-image, to an image under the function, no one else gets to go to B. Right? The idea of one-to-one function is if B is equal to f of A, no other pre-image goes to B. Right? It's B and A are uniquely paired. That's the idea of one-to-one. What this looks like logically would be that, okay, if I would have for all x1, for all x2, if I start off at different places, x1 and x2, which would be here in the domain side, that would imply that where they go to are different places. So x1 and x2 are from the domain. It's like, hey, if I have two different places in the domain, where do they go? Different places. They're never allowed for every single one of these that are different. They go to somewhere else. On the other hand, what would be the contrapositive statement of that implication? What would that look like? If I took the contrapositive of this implication, what would it be?
x1 equals f of x2.
That where you've gone to is the same place. What that means is, what would be the other one?
x1 equals x2.
They must have came from the same place. Hey, look, if they're the same on the right, they had to come from the same on the left. You actually don't have 2 points. You actually only have one. So sometimes it's easier to think about the first one. If you're at different starts, you end up at different places. The other one is if you end up at the same place, you had to come from the same place. They both mean the same thing. It's a one-to-one concept. This is also called an injection. The second thing we can talk about is onto. Onto simply says, now, to be a function, if I have students to chairs, I have a function here, does it matter that I have empty chairs? No, it's still a function. I don't have any restrictions on how many I use in the codomain. And onto then says, no, I'm actually interested in the chairs. I'm interested in the codomain. Onto simply says, every chair has somebody in it, right? Not only is it a function, but all the chairs have to be filled. And that particular statement would say that for every y that you have that's in the codomain, you can find an x that's in the domain such that f of x maps to that y. What this is saying is, this is my codomain. It says, everyone in the codomain has a pre-image. So all of the things on the right have somebody that's gone to them. What's nice about these two things is if I would put them together, and that would be called a one-to-one correspondence. It's also called a bijection. This simply means that F is 1-to-1 and it's onto. If I would look at that as a function, if f is a function, everybody goes. If it's one-to-one, that means whoever you go to is uniquely yours, right? That's what it means to be one-to-one. So this has to go to somebody that's uniquely his. This has to go to somebody that's uniquely his. This has to go to somebody that's uniquely his. What does it mean to be onto? To be onto means that there is nobody on the right that didn't have somebody on the left. All right, so there are no points that don't have a mapping. That is one-to-one and onto. If you look at it, what do I notice? It's a one-to-one correspondence. Every pair is unique. Everybody is used on the right. Now we can start to have a nice idea of what does it mean to be an inverse. So an inverse has to be an inverse function, right? It has to come backwards. So there's certain functions I would have to throw away. All right, compositions is just moving things. So the idea of an inverse under composition would be if a function goes this way, its inverse needs to go back. All right, now I can point out to functions that do not have inverses. So, for example, what if I had only 2 dots over here and only 1 dot over here, and it did that? Function goes forward. Now here's the question. Is there a function that goes from the right to the left? It can't. Why not? One's mapped to 2 places. That's not a function. So that's impossible. So going backwards is impossible. Can't happen. Why? Because it's not a function. One thing goes to 2 places. So this tells what, if I looked at that, I would say, wait, that's not one-to-one, right? So not one-to-one things are bad. On the other hand, here's another example. What if I had 2 things on the left, but I had 3 things on the right? And I did that. Well, that's one-to-one now. But, so this one goes to the second, the first one goes to the first. What's my problem? Can I go backwards? Is it a function if I try to go from right to left? What's the problem? What makes something a function? You're not allowed to split and go to multiple places. What's the other thing? If students are my domain and chairs are my codomain, to be a function, everybody must sit, right? I can't have a standing student. Everybody in where you're coming from must be used. Where is he going? Nowhere. Not a function. So if I have somebody going nowhere, that can't be a function. So it has to be not, right? This here, if it's not onto, it's bad. If it's not one-to-one, it's bad. And this is an or, right? What if it's not one-to-one? Can't have an inverse. It can't come backwards. What if it's not onto? Not going to have an inverse. Can't go backwards. It's going to be either not that or not that. Oh, okay. So what would be the negation of that statement? The or would become a and the nots would become not nots, right? So what would it mean? F inverse exists if F is one-to-one and onto. Why do I use that symbology for this little flag as a -1? That's not a power, it's a flag. Because what's an additive inverse? Times -1. What's a multiplicative inverse? -1 power. Right? So we tend to use this flag -1 to represent inverses because those are 2 classic inverses. So that's what's necessary for F inverse to exist. All right, now how could you check if you found F inverse? Well, what you do is you just say F composed with F inverse, whatever you say it is, better spit out X, and if you took F inverse composed with F, whatever it is, compose it, it better spit out x. And it has to go both directions. For college algebra, what did you do to usually find the inverse? Anybody remember?
Switch the x and y.
Just switch your x and y values. You first check to see if it's 1-to-1 and onto. All right? To be 1-to-1 and onto, it needs to pass the what to be a function, the vertical line test. To be 1-to-1, it needs to pass the horizontal line test. To be onto, you have to check what? If the range is the codomain. You have to make sure that the codomain and the range are the same, and then you would actually do it. Sometimes you have to create a partial function rather than a total function. You'd say things like, no, no, no. I'm only interested in these x's and these y's where my graph is. And then you limit it. Okay, the range is the same thing as the codomain. That limiting thing shows up a lot when we do things like, for example, when we had like the sine of x, right? Sine of x oscillates forever, right? Does it pass the horizontal line test? No, it doesn't pass the horizontal line test. This isn't 1-to-1. But do you have an arc sine? But we have an arc sine function. But it doesn't pass the horizontal line test. What do? They restrict it to a partial function. They say, for this partial function, the sign's stuck between what? Negative. Anybody? Wow, okay. So review your trig. Negative pi over 2, negative pi. Where is sine 0? Multiples of pi, right? So that would be back here, that'd be pi. So it'd be minus pi over 2 to pi over 2. You do a partial function, then invert it, right? That's how we go through these things. It's like you can't do it all. It's like, well, it has to pass these tests. Well, let's do a partial function and then deal with that. And so what is the, for example, the range of this object? Negative 1-to-1. So what is the partial function? From minus pi over 2 to pi over 2, from negative 1-to-1, that is what we deal with. What if it's outside of that? We do not deal with that. Right? We naturally limit it to what it does, and then we apply the idea of an inverse. Okay, so we can check inverses. We know when inverses exist. Not all functions have inverses. Other things that can be interesting to us is the idea of increasing or decreasing functions. Okay, what's an increasing function? An increasing function says that for all values, say x1, and for all values x2, if x1 is to the left of x2, then, well, if I would do a graph here, an increasing function says if this is x1 and this is x2, then your function heights, if I want to say that it increases, what should your function height do? Either stay the same or go up, and that's called increasing. And so that tells us that f of x1 is less than or equal to f of x2. And then this is called, if you see this thing, we call it increasing. As you go to the right, it stays the same height or goes up. Increasing function. On the other hand, if it was for all x1, for all x2, as you're moving to the right, you guarantee that your function goes up. We do not call it increasing, we call it strictly increasing. It always goes up. It doesn't allow you to pause. What's increasing? Pause or go up, pause or go up. What's strictly increasing? Always go up. What's the only difference between increasing and decreasing? As I go to the right, if I say it's decreasing, what should your height do? Go down. If you see that, we call it decreasing. And on the other hand, if I'm going to the right, and you strictly go down, you don't allow pauses, we call this strictly decreasing. It should be a review of calculus, because we talk about increasing and decreasing functions in calculus. What was your test for increasing and decreasing functions in calculus if it was a differentiable function? Its derivative would be what on an increasing function? Strictly increasing. Its derivative would be positive. If it's strictly decreasing, its derivative would be negative. But all that means is it meets these inequalities. So this allows us to take any function, any sort of rule, but it's going to be important, like when we look at this, well, it has to make sense. The inequality has to make sense. So these functions will be functions on real numbers. But for any one of these, we can talk about when is it increasing, when is it decreasing. Is it one-to-one? Is it onto? Is it a one-to-one correspondence? If it's a one-to-one correspondence, we could then find a composition inverse. This is all still review.